Hello class, welcome to the new recitation video for fluid mechanics. This week we will have 4 questions related to boundary layers and velocity profiles, and 1 question about flow in pipes. So let's start with the first question. This is question 9.25. Here we have a liquid with a given density, viscosity, and kinematic viscosity, and it flows tangentially past the flat plate. If the approach velocity is 1 meter per second, what is the decay velocity 2 meter downstream from the leading edge of the plate at 0.8 millimeters away from the plate? So first, let me show what these terms mean. First of all, here we have a flow stream, and we have an approach velocity as 1 meter per second. And when we say the leading edge, we call this area as the leading edge. And we have this flat plate. And lastly, the question says 0.8 millimeter away from the plate. So it is actually this distance, this 0.8 millimeters. Or we can actually call this thickness of the boundary layer. So what we need is finding the velocity of that liquid on that plate. Let's get started with first equation. First of all, we need to see if this flow is laminar or turbulent, or if it is in transition region. So to find that, we need to use Reynolds number. So as you know, if it is higher than 500,000, then we can call it turbulent, or if it is lower than 500,000, it will be laminar flow. So Reynolds number is velocity diameter divided by kinematic viscosity. And here the velocity is 1 meter per second. And here we were actually using diameter, but here we are going to use x, which is again a distance, a dimension, but it is the distance from the leading edge to x. So it was given as 2 meter downstream the leading edge. So for example, let's say this is our point. Or actually, let me use this point. So we can say that this distance is 2 meters. So we are using this x as 2 meter. Again, I want to repeat, it is the distance from that leading edge of the plate and this distance. Kinematic viscosity is 2 times 10 to the power of minus 5. And from here we can get 100,000 as a Reynolds number, and this means this is a laminar flow. So this means we need to use laminar flow equations. So to do that, in the question we are asked to find velocity. So we will need to use this solution, and you can find this in your lecture 20, page 12, and this is called Blasius solution. And given Reynolds number and the distance and also the thickness, we can actually get this ratio, which is the velocity at the given point divided by this free flow velocity, which is given as 1 meter per second. So that we need to use that relationship. So we have this term on y-axis, and we have another term on the x-axis. And as I mentioned, we will be calculating this velocity. So let's first find this term. So y is the thickness of the boundary layer, which was given as 0.8 millimeter or 0.0008 meter times square root of 100, which is Reynolds number, and x was given as 2 meters. From here we have 0.127. So this means we have y-axis as 0.127. So we can either use this velocity profile, this curve, to find x-axis, but there is a solution for that, and we can directly use another relationship. And this relationship is actually given in lecture 20, page 14. So we have this relationship. So here, the only unknown is u, which will be the velocity of that fluid. So u is, and this is the change of velocity relative to the thickness. So u will be equal to 0.332 times 1/2, which is u0 was 1 meter per second and x is 2 meters. We have Reynolds number and multiplied by the thickness. And this is going to give 0.042 meter per second. So basically, we need to find the liquid velocity 2 meter downstream from the leading edge. So from that leading edge, we have a 2 meter distance. And since this is a laminar layer, we can actually use this solution, which gives a curve. And on this curve, you can use this term, which is the thickness times square root of Reynolds numbers divided by that distance. And this gives the ratio of velocities. So the first velocity was given as 1 meter per second, and we needed to find u. And from the solution, we have a direct approach, which is given in your text in your lectures. So using that relationship, we calculated the velocity of the fluid at this point. This is question 2, 9.31. Here again, we have a thin plate with 6 feet long and 3 feet wide. And it is held stationary in a stream of water with a velocity of 17 feet per second. And this time we need to find the thickness of the boundary. And on when the Reynolds number is 500,000. And actually 500,000 is the limit of laminar and turbulent flow. But here we are assuming that boundary is still laminar. And what distance downstream of the leading edge does this Reynolds number occur? And lastly, what is the shear stress on the plate at this point? So differently from previous question, in the previous question we were given the thickness of the boundary layers and also the distance from the leading edge. But this time we have Reynolds numbers and we are going to calculate the distance from the leading edge and boundary of the layers, thickness of the layers. So we can directly start with Reynolds numbers because we already know that. And in laminar flow, and you can actually get this from lecture 20, page 11. Reynolds number is the velocity and velocity. X is the distance from the left-hand side of the plate or distance from the leading edge. And kinematic viscosity. So 500,000 is equal to 17 feet per second times x divided by viscosity. And this viscosity is coming from tables. I think table A something. So you can get it from that. And from here, the x distance is 0.359 feet. So we answered this question, which is the distance downstream of the leading edge. So for example, we can say this distance is 0.359 feet. The second question is the thickness of the boundary layers. So here we are going to use this curve again. So actually in this curve, we can see that we have that value, which is 5. So we can just see 5 when the ratio of velocity is almost equal to 1. So as it is also stated in page 13 in lecture 20, this is when u over u0 is equal to 99%. So we are actually using this relationship to calculate any boundary layer thickness. So in this condition, we have that five, and this is happening when y is equal to delta, which was the thickness. So we are actually saying that when y is at the delta level, it is when it is not the wall, when it is at the delta, which means when it is here, we will be using this relationship. So from this relation, when we leave delta alone, we will have 5x divided by square root of Reynolds number. And this is valid for laminar flow. And from here, delta will be equal to 0.034 inches. So I can further explain this question, this as option. So when y is 0, it means we are at wall. So at this point, u is also 0, as you can see here. When y is 0, u is also 0. But we are considering this option when y is equal to this thickness. So in that case, to calculate y or delta, we will be using this relation. And lastly, we are going to find the shear stress on the plate. And shear stress is equal to 0.332 dynamic viscosity to free flow velocity divided by the distance and square root of Reynolds numbers. This gives, we have dynamic viscosity. I think it is also not given, but you can also, of course, get it from tables. I will directly write it. The approaching velocity was 17 feet per second, and x was given as was calculated as 0.359. And lastly, the Reynolds numbers. And this is going to give shear stress as 0.262 pound force per square feet. And again, you can get this equation in lecture 20, page 15. Okay, this is question 9.41. For the hypothetical boundary layer on the flat plane shown, what is the shear stress on the plate at the downstream end, which is point A? And we are also given the density and dynamic viscosity. So the question clearly asking the shear stress at this point, which is the downstream end of this plate. So that we need to consider conditions here. So the shear stress is actually dynamic viscosity times change of velocity relative to the thickness. So dynamic viscosity is given 3 times 10 to the power of minus 5. And the velocity was given as 40 meters per second. So we have this incoming approaching velocity as the free system velocity. And we have this flat plate, and we just need to find shear stress at this point. So as it is clear from the equation of the shear stress, we need to use velocity at this point, because this actually means the change of velocity related to this thickness. So that we need to use this 3 millimeters thickness. And from here, the shear stress will be 0.4 Newton per square meter. We are now at question 9.43. We need to calculate the power required to pull the sign here shown if it is towed at 48 meters per second, and if it is assumed that the sign has the same direct force as an equivalent flat plate, which means we are going to apply direct force equations, which we derive from flat plates. And we are assuming an atmospheric pressure and a temperature of 10 degree. So first of all, in this type of question, we need to know if it is laminar or turbulent flow. So we can use this kind of equation, which is Reynolds number. So in previous questions, we actually used something like this. So they are basically the same, but with just different symbols. So the velocity is 48 meters per second, and the distance is 30 meters. And kinematic viscosity, you can also get it from tables, 1.41 down to the power of -5 square meter per second, which gives these Reynolds numbers, and it means we have a turbulent flow. So the main reason for determining if it is laminar or turbulent, we need to use specific equations for turbulent or laminar flows. So we first calculated Reynolds numbers. Then here we need to find the power required to pull the sign. And for the power, we actually use this equation, which is the direct force multiplied by velocity. And for the direct force, we are going to use another equation, which comes from the shear stress coefficient, area, density, square of given velocity divided by 2. So you can actually get the equation of shear stress coefficient from lecture 22, page 7. So shear stress coefficient, or we can call it direct force coefficient, is, and this is actually average direct force coefficient. So this gives the direct force coefficient so that we can calculate direct force, and then we can calculate the power required. And yes, this is coming from page 7. And the direct force is in page 8. So the direct force coefficient will be 0.523, and now square 0.06 times the number of Reynolds, minus 1520, again Reynolds numbers, and this gives coefficient as 0.002126. And now we can calculate the direct force. And direct force I'm not sure if I defined that, but it is the resistance of fluid to the motion, to the movement, and it acts opposite to the flow direction. So to calculate the drag force, we will be using this equation. We calculated this coefficient, and we will have area. I will talk about it later. And we have density, which is given as, it's also not given in the question, but since this is 10 Celsius degree, you can get this value from tables. So I will directly write 1.25 kilogram per cubic meter and the square of velocity. And it is divided by 2. So for the area, we can use the area of this sign, and we will treat it like a flat plate. So we have 2 times 30, which is this length, and which is this length and this height. But the force is acting both this side and also the back side of this sign, so that we actually need to use area for these 2 sides. This means we are going to multiply this area by 2. This is because this force is acting on this surface and also on the back of this sign. So we have this total area, and it is 120 square meters. The drag force will be 367.4 Newton. And lastly, we can get the power required to pull this sign. And here we will get 17.6 kilowatts. So we are at the last question, which is 10.8. And this is in the chapter flowing conduits. So we have a head loss from section 1 to 2 as 1 meter, and density friction factor is 0.01. The diameter is 1 meter and length is 100 meter. The flow is steady and fully developed. So we need to calculate the mean velocity in meter per second. And this is actually kind of an introduction to the pipe flows. So we had this 0.1 and 0.2, and the total head loss is 1 meter. If you remember from lectures, the head loss is calculated by FL V square over 2GT. So this means friction factor, length, square of velocity, 2 gravitational acceleration, and the diameter. And 1 meter is equal to 0.01. Length is 100 meters, and diameter, and we will calculate velocity. And we have 9.81 times 1 meter. So from here, velocity will be 4.4 meter per second, which is option D.